In this video, we're going to look at the local statistics processor within RAMP. So the local statistics processor uses a kernel of user-defined size or shape to iterate across an input dataset, and it returns the statistical value of all of the members of the kernel as it moves around the raster. So let's have a look at a few of these in a bit more detail. Here I've got my favorite terrain dataset, which is the mound that has the pockmark field on the top of it and some of these interesting rocky outcrops on the downslope of that mound. So we're going to use local statistics on this dataset. If I use the mean, it's pretty boring. It's the same as using the mean kernel processor. It's simply going to mean out and smooth the dataset. The same with the median, maximum, and minimum. There's no big surprises that they're going to return the median, maximum, minimum values of the kernel as it iterates across the input raster. Range perhaps is a little bit more interesting. So let's look at this one in a bit more detail. This is going to return the range of values within the input kernel. So in this case, I'm going to choose an input kernel size of 9 by 9, but in fact, I could also specify a kernel definition file. If I do this, it ignores all the multiplier values in the kernel definition file and only preserves the shape of the kernel definition file, and it will return the range or whatever other statistic I want from the members in the kernel definition file. Okay, let's give this a go. Okay, so here I can see the range of values across the terrain data set. In this area here around the mound, I have very low ranges or changes in value, but they get slightly higher in the pockmark field area here, and then are much higher ranges on the rocky outcrops towards the southwest. Let's look at a different one now. Let's look at calculating the standard deviation within a 9 by 9 kernel. So again, not hugely different from the range. This is just reporting what the standard deviation is. So it's reporting a very similar type statistic to the range in terms of how it would finally render it. Well, let's look at something a bit more interesting now. This is kurtosis. Kurtosis is a measure of the peakedness of a distribution. So this is going to talk about how peaked the distribution of values are within the 9 by 9 kernel. I should probably perhaps explain that a little bit more if you're not familiar with kurtosis as a statistical measure. So in this graphic I found on the internet, we have in the orange curve here a normal or Gaussian distribution. The blue curve is more peaked, so it's more pointy. So this is known as being leptokurtic. And generally, distributions that are leptokurtic have a kurtosis value of greater than +1. The green distribution here is known as being platykurtic, so it is quite fat and broad, and these generally have values of kurtosis that are less than -1. So that's just a quick explanation of what kurtosis actually is. It's the strength or peakedness of the distribution of values, and in our case within the kernel. So let's run that and see what it looks like. And maybe let's do something with the display here. So let's just cap that there. Okay, so you can see that the values within the pockmark region tend to have higher kurtosis, so they are more leptokurtic or more pointy. The values that are on the lower end are tending towards -1.6, 1.7, and so they are fatter, broader distributions. So what does this mean from a terrain analysis perspective? Well, if we look at this standard deviation map, you can see that the standard deviations are higher in the rocky outcrop area down here. But they're relatively low when we look at the kurtosis map. So that means that the distribution of values in here is quite broad, and we can see that by looking at the range map as well. So they have a broad distribution, but they have and fairly low kurtosis, so they're quite broad and fat. But if we look at the pockmark field, we have, and look at the standard deviations, we have kind of a mid-range sort of standard deviation in this area. So the range of values is, fairly normal, I guess. But that's probably the wrong word. But the kurtosis is higher, so the strength of the distribution towards the mean is stronger and more pointy. Let's look at the next one. So there is a processor method in the local statistics processor that allows me to generate all of the output statistic types, with the exception of, I believe, entropy. Let's check the help file to make sure that is the case. So it is going to return the mean, median, max, min, range, standard deviation, and kurtosis of the values. It does not calculate the next one, the entropy. So yeah, do that. Run this if you want to generate all of these statistics in one go. We'll skip over this one. The next and the last method in the local statistics processor is the calculation of entropy. Entropy is kind of a measure of the degree of randomness of the values within the kernel. So we use this often as a proxy for complexity. And you can use it on terrain datasets and other types of continuous univariate raster datasets. And we've used it often for looking at seismic data and the complexity of signals within a seismic dataset, and use that as a proxy for stratigraphic or lithographic complexity in those datasets. So it's quite an interesting statistic. Let's have a look at some of the inputs for it. So again, I specify a kernel size or a custom kernel. I need to create some histogram bins for that. So let's look why that is the case. So to calculate entropy, one of the things we need to know is the probability of the value of any cell existing within the, in our case, the kernel that we're putting over it. So we need to create a distribution curve as the basis for our assumption of what the probability of any particular value occurring in the kernel actually is. So that's why you need to specify the number of histogram bins as an argument to the method. So the higher the number of histogram bins that you create, the more sensitive the entropy classification will be. You can also choose to use an adaptive histogram. What that means is it will calculate the histogram distribution curve for just the values in the kernel rather than the values of the entire input raster dataset. So how is that useful? Well, it gives you interesting information if you care about very localized entropy and good contrast within the kernel area. But other than that, it's fairly meaningless if you want to think about the entropy relative to the entire input raster dataset. So let's go back and have a quick look at that entropy again. So I'm going to just choose the default here. I'm going to have a kernel size of 9 and 100 bins in my histogram to create my distribution curve from which I will assume the probability of any value within the raster it falls into. Okay, and I'm not going to use adaptive histograms. So let's run that and see what happens. Okay, it takes quite a while to generate entropy. It's quite computationally heavy, but here is the rendered version of the entropy dataset. And this is really quite interesting because it's showing that the pockmark fields here have are distinct in terms of their randomness, at least from these areas of the terrain. And the randomness goes up again in these rocky outcrop areas. So again, nothing too surprising given what we already know about the terrain data set, but an interesting statistical measure anyhow. You could also use entropy as a proxy for rugosity as well. So we've looked previously at the terrain analysis tools and some of the algorithms there for calculating the rugosity of a terrain. Entropy is another one of those statistical indicators that you could use as a proxy for rugosity. So we've gone through all of the statistical methods that are available in the local statistics processor, and I hope this has been useful for you.